Now, binary numbers, which are ones and zeros. So you might see numbers like this: 1 0 1 1 0 1 1, etc. It's the commonly known as a computer number system. So this is your digital number system that digital devices understand. They don't understand our decimal system. But with just ones and zeros, we can represent any number, even though there is just a 1 or a 0. The reason this is convenient for a digital system is because it literally represents two voltage levels: high voltage and low voltage, or no voltage. So we can easily send electrical signals, either high or low, to denote these digits. You can represent any number. It just might take a lot more digits than it would in your traditional decimal system. Each binary digit is called a bit. So this is a bit, this is a bit, this is a bit. They can only be ones and zeros. It's a base 2 system. So let's sort of decompose a number: 1011.101, base 2. Now, right here where I say base 2, that denotes that this is a binary number. This is not the number 1011.101. I know that because it has a subscript 2, which means base 2. If it had a subscript 10, it would mean it's a decimal number 1011.101, but it's not. It's 1011.101 in the digital number system that is called binary. So it is base 2 system. Again, this is a positional system. So here I've put the number into its little boxes to represent its positions, but the base of each of these positions is 2, and the exponent is the same as it was in the digital systems. So 2 to the power of 3 we know equals 8. 2 squared is 4. 2 to the power of 1 is 2. And look over here, 2 to the power of negative 1, that's the same as 1 over 2 to the power of 1. And 1 over 2 to the power of 1 is equal to 1/2. So same as over here, 2 to the exponent negative 3. Remember, when you have a negative exponent, that's the same as an exponent, but in the denominator. So that means 1 over 2 to the power of 3. And 2 to the power of 3 is 8, so that's 1 over 8. So I'm going to take this number and I'm going to take, here's the 1, here's the 1 from up here, here's the 0 from here, here's the 1 from here, and I'm going to multiply each of those by 2, the base 2, to the appropriate exponent. Now you can see here that I could save a lot of time if I don't write down all of the terms that have zeros. So you can see, for example, that this whole term goes away. This whole term goes away. You don't have to write that down, but I'm illustrating to you how to do this math. So you go line by line, solve this math. 1 times 8 is 8, so there's the 8. 1 times 2 is 2, there's the 2. 1 times 1 is 1, there it is, etc. And if you then take these fractions, 1/2, the fraction of 1/2 is 0.5. The fraction of 1 over 8, if you don't know off by heart that that's 0.125, you can literally go 1 divided by 8 in your calculator, and you'll get 0.125. Add up all of these numbers, and you get 11.625. So again, I looked at this number from the beginning. This was not 1011 because I see that it's in the base 2 system. Base 2 means it's a binary number. So what is that in decimal form? I need to go through the process of multiplying each of the ones by base 2 with the appropriate exponent, adding them all together, and you see that this number is actually 11.625 in our decimal system, which is base 10.